Hi, my name is Parker, and I'm going to talk about the work I did in Dr. Amanda Cook's research lab looking at nickel compounds for hydrosilylation. When we think about catalysis, we generally think of two modes, either homogeneous or heterogeneous catalysis. In homogeneous catalysis, your substrate and your active catalyst are dissolved in solution. This is great because you know exactly what is in the reaction, and this leads to higher molecular control. Unfortunately, once the reaction is complete, it's a lot more difficult to pull a homogeneous catalyst out. In heterogeneous catalysis, you have deposited your active catalyst on some sort of insoluble solid support, such as silica or carbon. This is great because it's really easy to recycle. You can just filter the catalyst out. Unfortunately, you often get limited molecular control due to the catalyst support, and you can get metal oxides or nanoparticles. What we look to do in the Cook lab is combine the two methods and isolate their pros using surface organometallic chemistry, which we homogenize a catalyst support and then deposit a known active catalyst upon it. First, though, we have to design an active catalyst, and we do this using homogeneous techniques because they're easier. For hydrosilylation in industry, we often see platinum used, which is a rare earth metal, and we see the ligands being N-heterocyclic carbenes or chelating phosphates. Now, we want to avoid rare earth metals, so we choose to use nickel rather than platinum, and we choose to use the NHCs because they're easier to modify in terms of sterics and electronics. Moving forward, we hypothesized that 3 nickel compounds would be successful, either the hemilabile asymmetric NHC, an alkene stabilized NHC, or a bis-chelating NHC. To determine whether or not these work for catalysis, we needed to synthesize them. And that was the bulk of our project. It was just determining if it was possible to make these things. In the first line, we successfully synthesized the alkene stabilized NHC using 2 different aryl substituents, either a styrene or a hexadiene NHC. In the yellow line, that second line there, we have the bis-chelating NHC, which we were also successfully able to synthesize. In the last line, we have the unsuccessful synthesis of the hemilabile NHC, which failed due to the bromine substitution for diphenyl phosphate. But we had catalysts to look at now, the alkene stabilized and the bis-chelating NHC. What we wanted to determine is if these novel compounds are more successful than commercial nickel compounds that you can buy online for hydrosilylation. To do this, we use the model reaction of diphenylsilane with styrene to yield either linear or branched hydrosilylated product. What we look to hope for is the branched product, which is more difficult to get in literature and is rarer in industry. Looking at the table then, the interesting results are highlighted in orange. Ideally, we get a high branch to linear selectivity and a high overall yield. What we saw in most of the commercial compounds is that you can get one of the two, but not both. So in the first line with nickel dichloride, you have really high branch to linear selectivity, but low yield overall. And then if we look at nickel tetrachus, which is the third line from the bottom, you get really poor branch to linear selectivity. In fact, we saw no branch product, but we got 100% yield. Neither of these cases are particularly useful for us because we want good yield and good branch selectivity. But our catalysts, the hexadiene stabilized NHC and the styrene stabilized NHC, provided both high branch to linear selectivity and high overall yields. What we saw from this was that we've made 2 compounds that work better than commercial nickel compounds for hydrosilylation, which is fantastic. Unfortunately, we were unable to test the bis-chelating NHC due to the COVID-19 outbreak. But this leads me into what we will be continuing to look at moving forward, which is testing the bis-chelating NHC for hydrosilylation, and additionally testing all of our catalysts for isomerization so that we can potentially do the tandem catalysis of hydrosilylation and isomerization. That's what I've been working on recently, and I hope you enjoyed the presentation. Thank you.